Hello everyone, I'm Rong from Brown University, and I would first like to thank the organizer of the workshop because this has been a really great learning opportunity for me, and it's also very helpful to meet people studying the same material. So today I will talk about the first principle calculation of the electric field gradient tensor of barium sodium osmium oxide. And I think you might have already heard a lot about this material on Tuesday. And what I want to mention is that in this work, we are not trying to develop a theoretical understanding of the problem. And what I will do is I'll try to explain and clarify why we think from an NMR point of view that there is a kind of structure distortion in the material, and why we think is orthorhombic, and how we use the NMR experimental result as a constraint and input values to do an estimate about the pattern and the magnitude of the distortion. So I will briefly review the material, which is the FCC double perovskite with FD1 osmium magnetic ion, and the infrared reflectivity identifies as a magnetic mode insulator with U about 3.3 electrovolt, and it has a ferromagnetic transition, but with a negative QY temperature and small effective moment, and the easy access is along 110, which is unique because the standard Landau theory with the cubic anisotropy term can only give you 100 or 111. And although the J effective is 3/2, the entropy is R ln 2, which means there's kind of some kind of source that leaves the degeneracy of the ground state. So there, because of the interesting phenomenon, there has been some theoretical models developed trying to describe the system, and in this model, they consider nearest neighbor anti-ferromagnetic and ferromagnetic exchange interaction.
Both nearest neighbor.
On different planes, because it's a FCC. Yeah. So, and also they also consider nearest neighbor electric quadruple interaction, which proved to be actually quite important in this system, and they can get the intermediate temperature quadrupolar phase with no magnetization. Actually, I also did a study on this model using, instead of mean field, using classical Monte Carlo. And I also find the intermediate temperature phase where there's there's fluctuation, Ising type fluctuation of spins on the two distinct osmium planes. That the C4 rotation symmetry is broken, but C4 rotation plus exchange of the two sublattice remains the symmetry of the system. And also another work using almost the same Hamiltonian also see intermediate temperature phase with distinct orbital occupation for the two osmium atom on different planes. So
what is on your vertical axis?
this one?
No, on the right-hand panel.
Oh,
y-axis.
I think this is occupation. This is occupation. So these three occupation should add it to
which become
add it to one.
at the
Yeah.
orbital order in temperature.
Yeah, I think this is the occupation. This successive phase.
V is on the left top figure.
What are the axes on the left top diagram? What are the axes?
V is
V?
These x's, what are the x's?
Quadruple.
This is temperature, this is T, and this is V, which is the coupling constant of this interaction.
And it scales in what? In temperature?
This T,
No, J, yeah, this is J and J prime.
this is our own non-unit. I mean, this is all parameter in their model that is unitless.
Yeah, but probably because they divided by J, which is probably the large interaction. So it's V over J.
V over J.
Yeah, I guess.
I'm not sure for this phase diagram. I'm not sure. I'm actually not sure for this phase diagram, but in their original paper, when they do a phase diagram, considering these three coupling, they did divide it by J. Yeah, in this, but I'm not sure here. Yeah. So yeah. So NMR experiment does see two transitions according to the spectrum. That there's firstly a development of non-zero electric field gradient at the sodium side that is revealed by a splitting of a single peak. And then with the lowering of the temperature, there are also two sides magnetically distinct, which after analysis actually revealed to be a canted order that is staggered along 110 axis. So actually this kind of successive symmetry breaking is also observed recently in another FD1 system, which is barium magnesium rhenium oxide, and it has almost same physical properties as the barium sodium, except that it has an entropy of R ln 4, which means it has a higher symmetry in its ground state. So back to the calculation in this work. So we are calculating the electric field gradient tensor on the sodium sides. So this tensor is a symmetric and traceless tensor. And so after diagonalization, all the information about the electronic environment around the sodium can be characterized by the largest eigenvalue VZZ, and also the symmetry factor that defined to be within 0 and 1. And also the eigenvector of the diagonalization is correspond to the principal axis of the electric field gradient. So NMR experiment has the ability to identify all these 5 irreducible elements that can characterize the electronic environment around the sodium according to the electric quadruple interaction.
And this was for what kind of symmetry? For what symmetry? I mean,
There's no symmetry. So actually, this asymmetry factor kind of represents the symmetry of the electronic cloud.
This is entirely EQR. You said NMR. That's not NMR.
No, it's electric field gradient.
It's only quadruple.
This is quadrupolar. Yeah. So, but NMR can calculate that according to the electric quadruple interaction, which is, in the its Hamiltonian is written as this with the EFG parameter nu q and the asymmetry factor eta in the so above the normal Zeeman splitting, because of this interaction, the spectrum further split, and then such as in this case, which is for the sodium, the splitting is different when the magnetic field is aligned with different direction of the crystal. So this is the splitting between different peaks. One is written in the EFG principal coordinate, so by doing the rotation, we will be able to deduce all these parameters experimentally. So this is what people start to do from 1950s, and in principle, any rotation, even if you don't know anything about the crystal structure, a rotation around along 3 perpendicular axes, we will be able to deduce all the parameters. So we did the rotation measurement along these 3 planes, and then we fit the data, and what we found is that the EFG parameter has to be with this principal axis along with the crystal, and the nu Q value is around 190, and the symmetry factor close to 1, which is quite large asymmetric value. So in this case, the question is what induced such a anisotropic distribution around the sodium atom? And one of the possibilities that because of the Kinted magnetization and the spin-orbit coupling, there might be some interplay between them that distort the electronic charge around sodium, and luckily WASP can directly calculate this parameter. So we did the calculation, and we found that without the magnetic order and spin-orbit coupling, the EFG value is always 0, which makes sense for the cubic case. And with the application of the magnetization and spin-orbit coupling, there is non-zero electric field gradient, but the value is too small to account for what has been seen in the experiment. So that means that apart from this charge distortion, there has to be a kind of structure distortion, so that that gives rise to this non-zero electric field gradient. So in order to see that, we tested some common distortions in double perovskite structure, such as elongation and compression of the 2 octahedral, and then rotation and tilt distortion, and the Glaser type distortion with fixed and flexible octahedral. So because the electronic environment on the sodium side is kind of dependent on the pseudopotential. So we tested 6 different pseudopotentials, and we found that the PP6 works best. And then by manually changing the bond length, that we find the distortion that actually can match with the value we deduced from the experiment. And that is
what is CFM?
CFM, the Kinted ferromagnetic order in.
What was called CAF on the previous slide?
Yeah, I think in some textbook it's called Kinted antiferromagnetic.
Sometimes
Yeah.
It's magnetic order that it does like that.
Yeah, I remember, but it's this abbreviation GGA plus CFM plus U. So what does it mean?
Oh, it means that the condition that I imposed.
Okay. So yeah, thank you very much.
Yeah. So if without the Kinted order and spin-orbit coupling, the full sodium atom in the cubic cell is all the same, but with the Kinted magnetization and spin-orbit coupling, it has 2 sets of the EFG parameters, which the nu Q value is around 20 kilohertz difference, and that's kind of can explain why we see the satellite actually has a broad line width, because it's much larger than the normal dipolar broadening, which is usually only kilohertz, but that line width is about 50 kilohertz in the experiment. So this might also play a role here. And besides of this,
Sorry, at which temperature are these experiments?
this experiment is at around maybe 10K, depending on different. Yeah.
What you're saying is that if you do the distortion following the Q2 mode, then you agree with what you're measuring in the experiment.
Yeah, but the DFT is always at 0 temperature.
I know.
Yeah.
You can always simulate the distortion, which is what you did.
Yeah.
You simulate the distortion of a phonon, and you look at what this distortion gives you for the. Okay, so I just wanted to know exactly which is these frequencies that we have. With the Q2 mode, do you know at which frequency?
4 Kelvin. It didn't really matter below 8 Kelvin experimental. We always saw the
Okay.
things 4
So
Kelvin.
it's not that low
No.
in frequency. Okay.
It was locked. Once you know the transition, it was.
Okay.
And besides this, we also see another 2 models which also fit, but not as well as the first one, which is firstly there are structurally distinct, 2 structurally distinct sodium atoms, and also another one is that the distortion we found on the earlier case and with the glazer type of distortion, but the main contribution to the matching experimental value comes from the magnitude of the first type of distortion. And so we also test the sensitivity of this EFG parameter for different magnetization, like ferromagnetic 110, and it doesn't change much. So it's not sensitive to the magnetization, which is kind of supported by a recent specific heat measurement that apart from the magnetic transition, they also see a field-independent higher temperature shoulder in the specific heat, and they did a nice analysis by decoupling the magnetic and non-magnetic contribution to the specific heat, and they see that this shoulder, higher temperature shoulder, is not reproduced from only considering the magnetization part from the specific heat. So this is a combined phase diagram from NMR and also the specific heat, and this insensitivity to the magnetic field can also be seen from NMR experiment. Our calculated local magnetic field is linear as a function of the applied field, and this makes sense because you have a constant susceptibility and a constant hyperfine coupling tensor, but for the staggered magnetization, which is defined as the difference of the local field experienced by the 2 sodium atoms, is kind of field independent, and this means that this pattern is governed by some higher energy scale of the material itself instead of a field-induced effect. And this is also true for the triplet, for the electric quadruple splitting, and which means that this is also not have a non-magnetic origin. So also we did measurement on the barium lithium, and the barium lithium is does not, even though it's isostructure and isoelectronic, it does not show the quadrupolar splitting, and that means it's probably is a perfect cubic, because even though the electric quadrupole moment of lithium is 1/3 of sodium, if it has any kind of structural distortion, it should still see it, but we did not see it. So these are the orbital and spin magnetic moment for the different structure and the magnetic order. So the spin and magnetic moment kind of cancel, but leaving a small net magnetization. And this is a spin density of two different magnetic order, which shows different pattern for the canted case and the ferromagnetic 110 case. And this is the partial density of states for the two osmium atom, suggesting a selective occupation of the T2G level for the two osmium atom. And also the band structure and also the calculation of the EFG value is insensitive with the U and J value used in the calculation. And
so these are the GGA plus U plus spin orbit coupling plus plus the magnetic order. These band structures that you're showing.
Yeah.
Okay, so this is the whole. It's because you don't have it on the slide. I wasn't sure.
Yeah. It's with everything. Yeah. So yes. So that's. I hope I have expand that why we think there's structure distortion and how we estimate it from the naive experimental point of view, and also. But there are some other remaining questions like the complexity of the hyperfine coupling tensor that does not reflect either atomic or the magnetic symmetry, which they should for the NMR measurement. That might mean some complexity from the orbital, spin orbit coupling, and also the reduced entropy of R-lon 2 that already happened above the orthorhombic distortion. So this is, I think, maybe something will be discussed in the next talk.
What is strange about this, the entropy of R log n?
So the ground state is J equals 3/2. The J effective is equal to 3/2, but the entropy is R-lon 2.
So it's like consistent with S1/2, but it should be, but you see 3/2. That's what you're saying.
Yes. Yeah. So even if if we consider there's kind of because the R-lon 2 is accumulated from both the magnetic transition and also the orthorhombic transition we see here. So that means even above the orthorhombic transition, it's already reduced to R-lon 2. That's what I think is kind of confusing here. But it's not seen in another,
Thank you very much for your talk.